right, Don, for some reason, is not coming through, so I'm going to step in here. Sorry, Don, and tell you that Tom does this absolutely marvelous newsletter once a week called Desalination. What's it called, Tom?
Water Desalination Report.
Water Desalination. That's right. I'm sorry. The memory is like a seed. It's no good. And Dawn has invited him to come because they were colleagues when she was still working in the water world. But he will tell us a little bit about his background. Uh-oh, Rita, you're not mute anymore. Thank you. Okay, Tom, it's all yours.
Okay. Well, thanks. And sorry about that, Dawn. But I'll just a little bit more about me. I'm based in Houston, Texas. I've been working in the water industry for my entire career, and desalination since 1980. I am, as we've said already, I write the Water Desalination Report. It's a weekly newspaper that covers the desal industry, covers projects, covers new technologies, and just basically anything I find interesting. It's published by Global Water Intelligence in Oxford, England, and I've been writing it since 2005. Before that, I was worked for CH2M Hill, one of the big consulting engineering firms, and I've also worked for some of the desalination equipment providers. I've lived in Houston for the last 47 years, but did a couple of overseas stints, one in Paris for a couple of years and one in the Middle East for 3.5 years. And I follow what's going on around the world in desal, and in the United States, if you follow desal, it means usually you focus on California, Texas, and Florida, where most of the desal is going on. And California has been very active for a number of reasons, some of which we'll go over today. And I think I'm just going to get started. Now, what you're going to do, I understand, Nancy, you're going to be moving the slides for me. Is that correct?
Yes.
So why don't we go to the first one?
Okay.
And as we've already established here, the title of the report, the talk is an overview of seawater desalination. And now I've divided things up into 8 categories here, starting with a few definitions to make sure everyone's understanding of the discussion is, or everybody understands some of the words that I'll be using probably fairly frequently. And we'll end up looking at the challenges in implementing a project. And nowhere has desalination been more challenging to implement than California. So it should be something that you all have probably read about a lot of these projects. Now, desalination, let's go to the next slide. And desalination is, well, it means different things to different people, but basically it's the removal of dissolved solids, primarily salts, from water. It can be seawater, it can be brackish water. In fact, for making semiconductors, they take drinking water and they go through a desalination system to remove anything that's remaining in it. So desalination is a pretty broad subject. Now, I've already heard someone mention desalinization. While that's acceptable, it's kind of an archaic way of pronouncing it. It primarily a European pronunciation that's pretty much fallen by the wayside. So I don't usually correct people, but I just, if you want to sound like a true desalter, as we call ourselves, we pronounce it desalination. And the salts or the dissolved solids in water, we usually measure by milligrams per liter or parts per million, ppm. They're basically interchangeable. There's some subtle differences, but it's the amount of salt in water by weight. And to put things in perspective, drinking water, or to be drinking water that's palatable, that's provided by most municipalities, it usually has less than 500 parts per million of salt. Brackish water, usually has a dissolved solids concentration of between 1,000 and 10,000. So when as I said, brackish or desalination covers a lot of quite a variety of applications, and there's a lot of projects. In fact, I think over 200 projects in California that desalt brackish water. They tend to be smaller projects, but there are a lot of them. The brackish water in aquifers in some of the lakes goes through the reverse osmosis system we'll be talking about, just like the seawater. But today's presentation is going to primarily focus on seawater, which has a dissolved solids concentration of 35,000 parts per million. That's about 3.5% by weight. And when you're desalting water, you divide it into two streams. You take a seawater stream, divide it into two streams, one of which has essentially fresh water with a TDS of less than 500 parts per million, and the other has the concentrated salts that include the salts that were in the water initially and the salts that were removed from the drinking water. So you're almost doubling the concentration of salt in the water. Next slide. Now, the whole discussion today is going to focus on reverse osmosis, which is a membrane process, and it's the primary way that seawater is desalted around the world. For many years, for the last 70 years, there were a lot of evaporative systems which boiled water and then condensed the vapor and used that as drinking water. But the cost of doing it and the electricity or the energy that was required has gotten prohibitive. So most of the world's desalination capacity has shifted to the membrane process. Now, what we've done right in this picture right here, we show 4 different membranes. We're going to be focusing on reverse osmosis. Now, reverse osmosis removes the salt molecules. We see that there is another membrane process that sometimes precedes it, and it's called nanofiltration, which allows some of the salt to go through, but prevents most of the other stuff from getting through. There are some projects in Florida, some in California, where just nanofiltration is required. It's kind of like a reverse osmosis light. It removes some of the bad actors, and if you've got a fairly low salinity in the water, in a groundwater, or maybe just some organics that you want to remove, it may be a less expensive alternative. Now, the ultrafiltration and microfiltration are two filtration processes that remove bacteria and sand and silt and other solids in the water. So you can imagine that with the reverse osmosis, if you're trying to get out the individual salt molecules, if it has all of this other stuff in the water, sand, silt, algae, bacteria, pathogens, and so on, you really could plug up the RO membrane. So it's important that you get those out first. And this just shows you wouldn't have these four membranes in series, but you might have either a microfiltration or ultrafiltration preceding a nanofiltration or an RO membrane. Okay, next slide. And first, we'll start here by just explaining osmosis, which is, well, in nature, nature prefers things to be in balance. And that holds true when you have a saline solution in this U-tube that we show right here. We have a saline solution on the right side, the dark blue, and the light blue is a fresh water.
Remember,
So
I said I had a.
And you have them separated by a membrane.
Or I'm gonna go upstairs.
And so what you see in this U-tube here is that if you have a semi-permeable membrane, this is essentially a reverse osmosis membrane, the pure salt will migrate through the membrane in an attempt to dilute that solution and make it all of a very similar salinity. So it'll continue to do that until it reaches, can you go back a slide?
Yeah, right. Sorry about that.
Okay, go back one more too here.
Yeah, sorry.
Okay, that's okay. So what we have right here is the salt will migrate through from the light blue to the dark blue to try to balance the salt concentration. And the difference in height is referred to as the osmotic pressure. It'll do that until it reaches a equilibrium. Now, the membrane prevents the salt from going through because the water diffuses or flows through it faster than the salt molecules can. So you get this natural osmosis that occurs. Now, if we go to the next slide. And for reverse osmosis, you apply pressure. In this case, we just show a weight. You apply a pressure to that higher surface and push down, and you reverse the process. You push the water through the membrane, and that's how reverse osmosis works. You produce this fresh water. Next slide. Okay, so a little bit about the membrane itself. It was developed at UCLA, although the process of osmosis was understood and invented back 200 years ago. There was never a practical way of applying it to desalt water until 1959, when two university researchers at UCLA developed the cellulose acetate membrane, and they patented it in 1960. Next slide. And the photograph on the left is a guy by the name of Sid Loeb. Sid Loeb and Srinivasa Surarajan invented the membrane, the RO membrane, and this shows the first commercial installation in Coalinga, California, which is up near Sacramento. They installed a unit and it provided drinking water for the community. And in fact, just in the last year, Coalinga is now reconsidering. It's grown quite a bit naturally, and with the drought and affecting the Colorado River and the other water supplies, they're considering going back to RO. The slide on the right shows the first seawater RO unit that was installed in Bermuda in 1974. Next slide. And this just, you'll see a couple of the comments that I make here are because there's a real California connection, which I'll go over in a little while. But this membrane we see, or this thing we see up in the top left, was the first, what we call a spiral wound membrane, one of the first advances in the technology. Now, this was a hand wound membrane that was developed by Reverse Osmosis General Atomic in San Diego, which has led to the spiral wound element we see on the right. This just shows the modern one. And that upper one, the company that made that was Fluid, well, Roga, as I said, they were bought by Fluid Systems and then Koch Membranes. And this was in a little glass case right outside David Koch's office, this first membrane here. Next slide. This shows another early membrane installation in River Valley, also in San Diego at a golf course. And this was installed because they had a hard time getting fresh water, and it was too expensive to pay for fresh water for the golf course. So they made 50,000 gallons a day with this unit. At the time, was one of the biggest in the world. Next slide. So just a little bit of history, but we see here that if we look at 1967, when that was the biggest in the world, we've come a long way. And about 2000, the industry really started to take off because reverse osmosis was proving more effective. We got a lot of experience here in the 80s and 90s. But still, there was a lot of evaporators going in, primarily in the Middle East. But around 2000, it really started to take off. And since then, almost all of the capacity that's been installed around the world has been in seawater RO. And I've got the units up there. That's to give you an idea here. It's 26 billion gallons per day of water is desalted. Now that's desalted both seawater and brackish water, but it's the cumulative capacity that's been installed since 1965. Next slide. And just a quick look at just recently here in the past few years, we've installed more new capacity in the past couple of years, with 2019 being the record. We've passed that up, or are about to pass it up next year, with getting 7 million cubic meters a day, and this is globally. So it's growing quite rapidly. Next slide. And a lot of the capacity that we've installed, most of the capacity is seawater RO, but there still are a lot more smaller brackish water plants. But in California, we've got these are the plants that are well, you see there's one or two that are under development. The South Coast one in Doheny Beach, that's actually at Dana Point, and the Cal-Am project, which was just granted one of its key permits a couple of weeks ago. You would think California, and they've tried and proposed a lot more plants than what are currently installed. We see one large one in Carlsbad that y'all are certainly familiar with in your neighborhood there. But all the rest of them are fairly small, and by world standards. I mean, some of the plants that are installed now in the Middle East are over 300 million gallons a day in a single plant. But one of the big issues in California has been the intake. How do you remove the water without sucking in marine life and killing it? And the Coastal Commission, who is the governing body in California, is extremely active in protecting the California coast. And the California Water Plan has a very rigorous intake requirement, and it's prevented most of the recently proposed plants from moving forward and slowed down quite a few of them. You see that the San Diego, the Carlsbad plant was kind of grandfathered in. They use a 1 millimeter screen, very fine screen. And the Santa Barbara plant, which actually was first permitted in 1991, but was dormant for quite a few years, and then was completely rebuilt in 2017, or in 2014, I think they started rebuilding it. It also has a 1 millimeter screen that was grandfathered, but most of the rest of them take water from wells that are beach wells, or in the case of the projects, the most recent ones in the South Coast Water Authority and Doheny and the Marina plant, which are nearing construction stage, have both been built with slant wells to get approval from the city or from the state. One plant that I have in here is this Marina plant. It was a plant that was built quite a few years ago, and I can't quite read it now because of I've got some of the people's faces covering it here, and I'm not savvy enough to know how to shrink that. Well, maybe there are they. Okay, that was built and in 1993 and ran for a few years. 1997, and ran till 2003, but then was shut down. But the city of Marina kept its permits up to date, and they're talking about starting that plant up again. But this gives you, these are the plants right now, the only seawater plants in California. There have been quite a few more proposed. There are some other ones that are in the very early stages, but I wanted to start by just providing that baseline. Okay, next slide. And the California connection, one of the reasons that, I spend a lot of time in California is because a lot of the companies and a lot of consulting engineers that I do a lot of advisory work on projects, and have been involved in a number of projects, one in West Basin, one in Santa Cruz, one in Marin, as they were trying to develop it. So I've been out for those projects and others. But there are a number of companies, desal companies, that are headquartered in California. And that's really where well, first of all, we know that's where it lists the desal innovations at the top. That's where the membrane was invented. The spiral wand element was developed, a number of other firsts. And then some of these companies that are world-class companies. In fact, this Energy Recovery Incorporated makes well, they probably have 80% or more of the seawater desal market in the device that they invented to recover energy from the system and reuse it. Some of the biggest, two of the four biggest membrane companies are headquartered in California. Next slide. So I'm going to start here and just kind of walk you through a desal plant, show you the basics. And this first slide is the most basic diagram that I could come up with, showing the elements of a desal plant. And we see, first of all, the seawater intake, which is a screening mechanism. We'll look at some of those in a little while. Then the water has to be pre-treated. This is where you get out the solids, the sand and the silt and so on, so that the membrane can do its job. Then once you go through the pre-treatment system, you then pump it up to something in excess of the osmotic pressure of the water. In the case of a brackish water system, you might pump it to 200 to 400 PSI. In the case of an RO membrane, it would be, in the case of a seawater RO system, it would be 800 to 1000 PSI. The water that goes through the membrane is considered desalted. Then a little bit of some minerals are added back, some calcium and some other minerals, just so it tastes better. And then it becomes product water. Meanwhile, the concentrate, which is all the brine, and remember the 60,000 to 75,000 milligram per liter salt, is discharged back to the sea. Now, the next slide shows the typical deviation that you have for a seawater RO plant. As I just said, for a brackish water plant, you're only operating at 200, at the most 400, but probably 200 to 300 PSI. For a seawater plant, though, if you're operating at 800 PSI, once you pump it through the membrane, the desalted water comes out at just 10 or 20 PSI, pretty low pressure. And all that pressure is stored in the concentrate. So that what they've done to make seawater RO more energy efficient is they take that high pressure, run it through essentially a little turbine, use that energy to boost the high pressure pump, so they're able to recover well over 50% of the energy. This is a way that we keep the energy cost down to a much more viable range. The concentrate is then discharged. So this is what the elements in this particular schematic are, what you'd see in a seawater RO plant. Now, the next slide here shows another change that's also made for most seawater plants. In fact, the ones in Carlsbad and Santa Barbara certainly have this. They take the solids, in the pre-treatment system. You might remember back to that first slide where I showed all that stuff that was removed by the ultrafiltration or the microfiltration membranes. Well, you got to get rid of that. And that goes to another residuals treatment system and then is trucked away as sludge. Meanwhile, the water that's recovered from that then goes back into the system. So it's all an attempt to keep this thing, without wasting any water. And once you've treated it and once you've pumped it from the sea, you want to turn as much of that into drinking water as possible. Next slide. And then to just show you about how this water balance here, this is what a seawater RO plant you can expect out of it. For every 100 gallons you put in, you expect to get about 45 gallons of product water and 55 gallons of brine. The sludge is just solid, so it really doesn't factor in that equation. This is what we call the recovery. So the system, and some people say an RO plant is inefficient. It only recovers half of the water. Well, that's true, but the fact is that when you start concentrating that brine up as high as you do, once you get over 60 or 75,000 milligrams per liter, it gets very expensive to recover any additional water. So that's a concession that has to be made, and we'll talk more about that later. Next slide. I've shown you just a block diagram in the previous slides. This shows what a actual functioning plant would look like. Starting in the upper right, the water flows from right to left and then down and then through the system. So we're going to quickly break this down to its component parts. Next slide. and the first being the intake. So next slide. This shows what a typical seawater intake looks like in most of the world. You have these intake heads, which have screens on them, and they range from 1 millimeter in some plants, especially the California plants, to as much as 2 inches in some other plants. The water is then pumped to shore where it's treated in the desal plant we see on the shore. The drinking water goes out one end and the concentrate goes back out to the sea and then is discharged through some diffusers. We'll talk about those in a little bit more detail later. But this just shows you what I would say 80%, 85% of the plants around the world, how they're configured. You try to get the intake out in an area that is not very biologically active or less biologically active than what you find right in the near shore. In some cases, it's 200 or 300 meters. In some cases, it's 2 kilometers. Oh, sorry, it's a mile and a half or more. Well, a mile and a half at the most, probably. But you go out a long way because you want to get out into the, as I said, where it's less biologically active and you're less likely to get the most the juvenile or organisms that you might get from fish that spawn near shore. Okay, next slide. The gold standard is this project is in Fukuoka, Japan, and it's a fairly large plant, but it's in a bay. It's in a fairly enclosed bay. And what they did is they excavated a big area. It's a couple of football fields in the sea, and then laid these pipes down and covered them with sand, and then let the water cover the whole thing. And so the water has to percolate through the sand into the pipes, and then it goes on shore. Now that's a great way to do it because you're not interfacing with the fish or marine life at all. Next slide. But it's pretty impractical in most places. It's always looked at in plants, but there's only one large plant, the one that you saw right there, that has done it successfully. What's being used in a couple of plants in California is what's called a slant well. It's kind of a variation of that, where you hydraulically drill a slant well out from onshore, out under the seabed. And you see the seafloor, the water percolates through the seafloor into the well. And again, you're preventing it from catching any fish. The disadvantage of this concept, of this whole arrangement, is that you're not able to build a large plant because these wells just, they don't work quite as nice as you'd like them to. Next slide. This is a more common intake. This is what the plants, a lot of them have on them on the offshore intakes and some of the nearshore intakes with a wedge wire screen. Next slide. I guess I'm better get moving here. I don't want to. The next part of the project is the plant is a pretreatment system. Next slide. And in some cases, it uses membranes like the ultrafiltration membranes. This is a plant in Sydney, Australia, which uses the same ultrafiltration membranes that I showed in one of in the first slide, or in the definition slide. Next slide. Then it goes on to the pumps and the pumping. This is where you pressurize the water and pump it up to 1,000 psi. Next slide. And you see some of the high pressure pumps, and these yellow devices are the energy recovery devices. Those yellow ones are the ones made up in San Leandro, up in the Bay Area. Next slide. And shows some other various plants. All look, they're all constructed differently depending upon the availability of space. This one on the right is Sand City, a little place up in Northern California. Has a very small plant, but pretty confined. The one on the left, I took in a project in Saudi Arabia, and you see it's a lot more open. But again, you see the pump. It's this gray box and this blue thing are the pump and the energy recovery devices in the back. Next slide. Then we go to the RO membranes. The next slide. And we just see a couple of configurations. The one on the left is in Perth, Australia. These racks are so big, they often construct the buildings around the racks. The one on the right is in Melbourne, Australia. Next slide. And then the concentrator, the brine, that's then from once you take the finished water and you post treat it, and it goes to it's used. Then we go to the outfall. Next slide. And this shows what you do with the brine. This is one of the other big areas. The intake and the outfall are the two big issues. And what you do with the outfall is you take the brine, and the goal is to mix that water as quickly as possible with the seawater, because some fish, marine life species, and some seagrasses, certain types of seagrasses, are intolerant of salinity changes. So to minimize the salinity change and keep it as close to ambient as possible, we take the brine and we discharge it through a nozzle, and it's jetted up and out. This allows it to mix with the seawater, and because it has a lot of salt in it, it's denser and it'll settle to the bottom. So you want to push it out and up so that by the time it gets to the bottom, it's all been assimilated or dissolved in the ambient seawater. And the goal of most designs is to, within 100 meters of discharge, to have it be assimilated into the seawater, so there's a minimum difference in salinity. So you're not increasing the salinity by more than 2% at the within 100 meters. Next slide. And this just shows these nozzle diffusers in red. It shows, and they usually put the pipe underneath the seabed, and then you see the nozzle diffuser. On the upper left is a study that they did using a dye to see what kind of dispersion they get with the nozzle. And on the bottom, it shows one of the nozzles that was in service for 1.5 years. It shows all the barnacles and the growth on it. Next slide. So there we go. Those are, and just wanted to point out that a seawater RO plant is a pretty complex project. And if you look at the pre-treatment system, that's analogous to a conventional water treatment plant. And here we've got all the rest of the kit built around it. It's operating with very corrosive waters, high pressures. Safety is a big issue, a lot of expensive materials, and that's part of the reason it's as expensive as it is. Next slide. There are a lot of new developments, and they're pretty esoteric. And so rather than go through them, and when Dawn and I talked about this, I wanted to cover some, but without this cursory introduction, it would have not made a lot of sense. But let's suffice it to say that a lot of the stuff we see in the regular world, the changes in the digital desal, there are a lot of this artificial intelligence, or AI, is being used, new sensors. There's a lot more monitoring going on so that changes can be made as with temperature changes, salinity changes, energy costs as they go up or down. There changes must be made. So a lot of digital desal. They're looking at new membranes, make them more strong or more robust, produce more water. They're even looking at 3D printing of membranes, and there's a lot of work being done in the university. Brine concentration, some plants are considering zero liquid discharge, which means all of the brine is desalted and you produce a brine that can be reused. The problem with this is it's very expensive, and prohibitively so in most places. And the stuff you're recovering is pretty inexpensive commodity chemicals. Salt, as one glaring example. Another one is calcium sulfate or gypsum that you make sheetrock from. But even the salt from one big plant like Carlsbad would inundate the market, the local market. So it just isn't very cost effective. There are other new form factors, new designs being looked at. The problem is that the desal is pretty efficient the way it is. Integrating renewables in the Middle East, most of the big plants over there are using photovoltaic energy at a cost of less than 2 cents a kilowatt hour. So it's really changed the cost of desalination in the Middle East. decentralized systems. These are smaller systems. Rather than building the big monstrous Carlsbads, why not build smaller systems? You know, there's like everything, it's something you have to evaluate, because there are, in some cases it makes sense, in some it doesn't. There's no one simple answer here. Next slide. And one of the big problems in California is the permits. You know, there's these 2 pages of permits I've got here that have over 27 agencies that provide over 40 permits, or up to about 40 permits. And this shows something, and this, I got this from the Doheny project that's being done right now. And in fact, it's going before the state lands agents, the state lands agency on Friday. But this shows some of the plants. Now, one thing, next slide. This is a big issue. In fact, this has been one of the most contentious issues of the last couple of plants, is the environmental justice issue. The fact that desal plants are being constructed in areas where there are a lot of impoverished people. And you know, there's certainly a push to make sure that it's not being done unfairly. You know, most of the plants that have been proposed in California have been proposed where there's an existing power plant, so they can share the intake and outfall. So I know for a fact that, you know, because that was the state of the art back in 2000, 2002. It wasn't until about 2003 that the state started saying, wait a minute, if we put in a desal plant, it's got to be a standalone facility. But until then, almost the only place to put a desal plant that made sense, because you had, the land was you know, permitted, or it was what am I trying to say, the only place that it made sense was near some other industrial activity. You didn't want to put it in a subdivision or a neighborhood if you could help it. So it was put in an industrial facility. This has led to issues, though, in California, trying to mitigate the potential impacts. We've got project right now in Corpus Christi that is just beginning to deal with this environmental justice issue. So it's one of those tough issues, because it's not an engineering problem. You've a lot of work is required to satisfy all the parties. But anyway, that's the next page, just shows the remainder of the permits that you needed for a project in California. And you know, some of them, admittedly, some of them are just, you know, fill out a form and you get a permit, but some of them require literally, you know, years of negotiation. The plant in Marina that just, you know, it's been being discussed for over 20 years. And there's been numerous submittals for permits, but it's been delayed and delayed and delayed. Next slide. One thing that you try to do when you're looking at desalination is you look at the overall water portfolio. And if we look at San Diego's water portfolio in 1999 or 1991, we see that most of the water came from Metropolitan Water District, which is a big wholesaler in the LA area, and they import most of their water from Northern California. So that's not a very sustainable solution. In fact, by the time you pump the water to San Diego, to parts of San Diego, you take more energy than you do for a desal plant. But they've been making changes. They've been diversifying their portfolio. They've looked at conservation. They've looked at recycling. They've looked at groundwater, all the displayed at the bottom there. And we see the Carlsbad plant represents that 10% of the water in San Diego. And it's the only source, it's a new local source. So if they get cut off, if there's an interruption due to a tsunami or an earthquake, they would be without the water from Northern California. So that's one of the reasons that people look at desalination, to diversify that water supply portfolio. And they intend to do it even more, as we see by 2045. Next slide. And when you're looking at desal, people always talk about the cost, because the cost is clearly higher. But this was a study that was done in Israel. Israel built its first large-scale desal plant in 2005. It went online, and they had such hard water that you couldn't get a warranty on your washing machines, on refrigerators. ice makers, because they would corrode because of the chlorides in the water. Since from 2005, they now in 2022 have about 80% of their water provided by desalination. But even by 2008, when they had their third plant operational, they already see a reduction in the chloride concentration in the groundwater, and the hardness as well, which allowed them to they calculated that it increased the value of the desal plant, and it was in an amount that was almost 45 to 65% of the cost of the desalination plant, and it resulted in beneficial or improvements in first of all, not only the water supply reliability, but they were able to grow more food, more crops per acre. They reduced their aquifer withdrawals. It added to the amount of water that they could reuse. It reduced the hardness, allowed them to get back some of these warranties that the rest of us take for granted. And they project, and they haven't done a new study recently, they're working on it, but they show that it's going to have a significant reduction, or it should have already. Likewise, studies that were done prior to the Carlsbad plant showed that it could have an impact, and people here in Texas might not recognize the units, but in California, they said 145 to 100 or to $175 an acre foot reduction in the cost of water. Now that's not as significant as they saw in Israel, but remember, this plant in California, or the Carlsbad, represents only 10% of the supply, rather than what's done in Israel. Okay, next slide. Desal's challenges. This is a slide I didn't want to start with this, because this is probably what everybody is most interested in. These are the challenge that you have when you're doing desal. The first one is planning. When do we build it? There's countless cases of people building a desal plant, and within the same year they build it, it starts to rain, or in some cases they have floods, and people say it's a white elephant. Also, where do you build it? The water, the water doesn't always rain and fall where you want it to. And the other thing is, how big should it be? Should it be 10% of our supply, or in the case of Israel, can we justify 90% of it? Siting is a big issue, and with environmental justice, we're seeing new groups that are adding their voice in opposition to where plants are located, which certainly, when you're trying to locate a plant in a seawater plant, the first thing you got to do is got to be close to the sea, because you need that seawater, and you've got to pump it inland. In the case of, and you're pumping a lot of water from the sea, twice as much as what you're actually going to end up as drinking water. So you want to have it as close to the sea. Most of the plants are within a kilometer, or within a half a mile to a mile of this coast, and that's where most people want to live, close to the water. So you've got some opposing issues that you've got to reconcile. The intake, we've talked about. That's when you're doing a fatal flaw analysis, that's usually the first thing you look at. Is there a place I could put an intake without doing any real environmental damage? Desalination is the most expensive way to make water. It needs a lot of electricity. But there's, sometimes at the end of the day, that's the only alternative. And when you, and that cost usually doesn't take into consideration some of the benefits that you end up seeing either. Financing, who's going to pay for it? Most municipalities don't have deep enough pockets. That means the private sector has to step in, but a lot of people don't like the private sector involved in water. I personally, I can see why that might sound bad, but sometimes there's no other alternative. And if you have a good contract in place, it's a viable alternative and is all around the world. The largest plants in the world, and most of the large plants in the world, are built even in Saudi Arabia and the United Arab Emirates, are built with private financing. The brine has to be put somewhere, it goes back into the sea, it sounds bad, but I assure you that there's been a lot of science around it, as there should be. And I have seen no instances of any damage other than, and not even that, it's not usually considered damage. It's just a relocation of some species of marine life from the immediate discharge point to outside that zone of initial dilution, which is up to 100 meters. Once you build a plant, you have to optimize it, and it's not cheap to run. So those costs get factored into the cost of water, but it is more complicated. And then energy, integrating renewables, desalination. It requires 2 or 3 times as much energy as a conventional water treatment plant would require, but it also provides usually a higher quality water because of the way it's produced. And if you can use renewables, that in most markets is bringing the cost down. And in California, the implementation timeline, if you decided you needed desal in California, it's going to take at least 7 years to get a plant on the ground and making water. Even in a place where you're not constrained, like you are in California, it's probably still going to take you 3 years, maybe 4 years to get one in. So it takes a while. There's a lot of economies of scale to desal. That's why a lot of these plants tend to be big. And next slide. And I've got pictures of the California plants, but I had those in there if I finished early, and obviously I didn't. So we'll forego those pictures, and you can look at those in your convenience. But in the meantime, I guess I'll turn this back over Nancy. If there's any questions, if it's not too late, I'll be happy to answer anything I can.
Okay, the first question is, how much energy can you save with 2-stage RO?
Well, a 2-stage RO actually costs a little bit more in terms, well, okay, now that a 2-stage RO, you can save some energy, but in some cases you need a second stage anyway. And that's kind of a complicated answer. I mean, I'm not able to answer that really effectively without looking at a diagram. But it's, as far as energy savings, desal plants, in my opinion, we've gone about as low as we can go in energy. And some plants need 2 stages. Some plants need sometimes what they call 2 passes. It goes through the RO membrane twice rather than in a stage. And a lot of it has to do with how you design your plant. There are trade-offs with almost everything you do, and certainly how you configure it in terms of stages. So it's not an easy question to answer.
So Tom?
Yes.
This is not okay, because you can hear me now. So the reason you would do a 2-stage typically is to just get higher recovery, right? But it's going to take more energy. So I don't know if that's the person understood the reason. That's the reason you would do it. So that's to get higher recovery. 2 passes is usually to get better water quality. If you've got real high salinity. Well, both of them take more energy.
Yeah, but with today's membranes.
Oh, and I used the wrong word. I meant 2 pass.
Oh, okay. 2 pass. Well, I've got a real nice slide that shows about what that adds to the cost. But even with 2 passes, a lot of plants are built with the ability to operate at 2 passes. But sometimes they only operate 25% of the total flow as 2 pass. Sometimes, and then depending on the temperature, because membranes, the warmer the weather, the warmer the water, the warmer or the better the membranes perform. In fact, 1 degree C increase in temperature increases performance by 3%. So at different times of the day, you might increase more or less of the water as a single pass, or as more or less of the water as a double pass, excuse me. So there are cases. There are also cases in California and in Israel are 2 good examples where you want to get boron out of the water. and boron is something that can affect horticulture, citrus trees, especially the ability of citrus fruit to ripen. So you want to get the boron down below as low as you can, practically. In some cases, it necessitates 2 passes. In some cases, part of the water might even go through 3 passes, as in a couple of plants in Israel. But these are fine tuning. It depends upon the water, a number of issues.
Okay, let's go on to the next question.
Okay, just 1 second. Let me go back to it. Where is the sludge trucked, and is there any use for it? If not, where is it dumped?
Well, it's usually dumped in a landfill. I think a class 2 landfill. I'm not it has to be a landfill that can take water with some salt content, because or sludge that is been subjected to some salt. But it's not particularly difficult. There's usually municipal landfills that can handle it quite readily. Most of it is just the branches and leaves and some of the larger matter that gets caught in the intake screens. You also can get some of the chemicals that might discolor the water. There's one of the chemicals you often use in a desal plant sometimes when there's the water is very turbid, is a chemical called ferric chloride or ferric sulfate. And if you don't get rid of that and remove it from the water, it can add a reddish tint to some of the discharge. So, and that aesthetically, it's not very pleasing. It doesn't really do much harm, but it is a nutrient. And there are some people concerned that by adding the iron nutrient back into the seawater, which is nutrient deficient, you're now going to provide a source for algal blooms to occur. So it's, there are a lot of steps taken to make sure that you're recovering that stuff, and it's treated, concentrated to the greatest extent possible, and then disposed of properly.
Okay, next question. How much energy did you say that heating the water saved for RO? They have a parabolic mirror with a RO tube in the focal point.
Well, yeah, we're talking about just a couple of degrees, and a parabolic mirror can, heat that really can get things hot. It's not economical to heat water up in most cases. In very few cases, in fact, in some places in Saudi Arabia where they pump it out of the ground, it's too hot. Well, not just Saudi Arabia, but places where they pump it out of the ground, it's too hot in the groundwater and has to be cooled. But heating water is not something you want to do. To heat a bulk solution like that takes a lot of energy. So most of these membranes are designed, and you use different membranes based and different pressures depending upon the temperature range that you're operating at. So
Okay, so they have,
No, Grace, no, we're not going to do it. We're going to go back up to the question that was asked by Rita about since the Doheny intake plan is more favorable to the environmental community, do you think you can get some environmental support for desal?
There is environmental support for desal.
Yes,
yeah,
there is.
There is on Doheny. It's got a lot, because they're doing a couple of things. Not only are they using the slant well, they're also discharging their brine with the wastewater discharge from a wastewater plant. So what that means is it's diluting the brine and bringing it closer to seawater concentration. So when it's discharged, you minimize the impact. So, and again, there are side issues to all of these things, but I'm not. But anyway, the Doheny plant. The reason Doheny plant is going ahead is, as Dawn said, because there is environmental support for it. There are still people who don't want it because they think it's costs too much, and they think some people who still say they don't need the water. I mean, that's a constant challenge. And the reason there are also people who oppose the plant up at Marina, but the Coastal Commission, even though it didn't like aspects of that plant, they approved it because when looking ahead, these water planners don't just react to a 1 or 2 year drought. They look at long term and they look at trends, and they for the state requires them to look out as much as 50 years. So when they look out with population growth and they try to do their planning, what's things going to look like down the road? They decided, the Coastal Commission said, that we see no viable alternative to desalination. That's the wording in their recommendation to go ahead was, even though we disagree with some of the aspects of it, we see no viable alternative, and if they need a water supply, so this is what we've got to do.
And I think that's going to happen a lot in the future. The next question is there government oversight of the costs of desal? And second question along there, are private investors making a lot, perhaps too much, money on these projects?
Well, I think you'd ask Poseidon that. They'd say no. They lost $100 million in their development costs to develop Huntington Beach. So, I can't, how much, I don't think so. I mean, from the companies that I see and the companies that I work with, I don't see these companies. I mean, it's a very competitive market. These plants are built, or they're millions of dollars goes into just the cost estimates for a plant like this. And it's a very complex plant. When you take in and look at all the permitting, those costs there, I mean, it's that's a question. And is there government oversight? Well, it's even worse than that. There's public oversight. I mean, people aren't going to pay the water bills if they go up. I mean, people like me, I don't want my water bill to go up, but you start looking at the reality of it. And as I said in the intro to my bio that I gave you, when you're looking at new water supplies, you have 4 options. You can conserve water, you can store more water, or you can reuse water. And the 4th option is you need new water. And the only new water is really desalted seawater. And if you're in San Diego and you're relying on all of your water supply from Northern California, is that a situation that you want? You want some water that you control the water supply over. And there's no other way to do it that I've seen other than desalination. So it's, a lot of people look at desal and I think it's perhaps a right way to look at desal. It's like an insurance policy. You've got to have some in place. If you're a coastal community that doesn't have any local water supply, it makes sense to have some local water supply and an insurance policy. And that's how I see desalination, as an insurance policy. And it's up to you, or it's up to the community to decide how much insurance are they willing to pay for. Do they think that, and what are they willing to pay for? And, if you want to water your lawn, if you like a green lawn, if you like, it's, and some people think it's frivolous, we don't need it, we should put in gravel. Well, that's up to the community to decide. And the community has a big voice in desal plants, and nowhere more so than California. I mean, I was involved with the Santa Cruz project, and they did a pilot study. They spent a lot of money, looked at it, tried to design every bell and whistle that we could to minimize it. And it was a small plant. It was just a few MGD. And at the end of the day, the citizens said they didn't want it. And then what did they do? The city held an open house, and they had like a science fair in a parking lot to invite people with good ideas for improving the water supply to come in. And it's no surprise it didn't go anywhere, because there is no alternative. But it's up to the community to decide what they need, what they're willing to pay for. So it's, you know, I try to stay out of those discussions too much because you can't win, or at least I can't win. I just try to help people come up with make sure they're making an informed decision and designing it with the latest technology that it has the best possibility for working.
Okay, Tom, and the final question for you today, which is going to cause you some work, I'm afraid, is do you have any references or papers on some of the desalination efforts worldwide? And I'd like to put in a pitch here for your newsletter because you have some outstanding information in it about what's going on worldwide. And I would like to know if there's some way we as a committee could get our hands on some of those stories and not violate your rules about not publishing or sharing your information.
Well, if there's something in there that you think your people should know about, I mean, I don't object to you taking snippets or using pieces of it and just mention where you got it. But
sure.
Yeah, I've got a lot of stuff. That's all I do. I mean, that's my job, is to read everything and to go to a lot of these plants and to be involved in a lot of these plants. And by the way, I do it independently. I'm always I'm not trying to buy or sell anything to. It's a matter of just objectively trying to review the plants and other people's work, because that's what I do. So I've got a lot, but I mean, how you'd quickly be inundated if I started sending you stuff, because it's a lot of it. I mean, a lot of it is very technical, and it's some of it's daunting, but you know.
Okay, not the way technical stuff. Let's cut out the way technical stuff.
Well, but unfortunately, the stuff that isn't way technical often is poorly done. I mean, there are so many myths and misconceptions about desalination, about what it does do and what it doesn't do, and how much it costs, and what the brine does, and and you know, I heard, and this comes from people who should know better. You know, I heard a state regulator who was interviewed on NPR kind of offhandedly say something that was very wrong. And, you know, once it's out there, you know, it's hard to take back. It puts, you know, people who may not like it or may be opposed to it for whatever reason, that's all they need, is just a little bit more fuel. I mean, it's difficult. In fact, and I told Dawn that putting this presentation together today, it was fairly basic, but sometimes taking these complicated things and trying to accurately represent what desal does and doesn't do in a simple way is harder than writing about it in a technical way sometimes. And the stories that I write in WDR, that's what I try to do. I take complicated stories, I try to dumb them down so I understand them. You know, it's like I always say, it's like going to school every day, because I read some of these technical papers by really good researchers and try to figure out how can and to understand it and simplify it takes, you know, forces me to really get into it in many cases. So, you know, but if you do see something in WDR that you think is interesting, or you have a subject that you're interested in, I've probably written about it. And if it's a plant, I've probably been there, and I've, you know, and many times I've written about it too. So,
Well, you have been extremely gracious today. I wanted to tell you that I thought that presentation on desal was the best one I have ever seen. And I've been down the road a little bit with desal. So I want to thank you so much for your time. It was so generous of you. And I'm afraid you're going to hear from us again, Tom, because you're too good to let you go away only one time. We'll have other questions for you. Yes.
Are we going
Connie.
to have, Tom, may we have a copy of your presentation?
Yes, I told Nancy and Dawn that if they wanted to make a PDF of the slides, they
Please.
could, and so you can have them.
Thank you.
Oh, well, actually, I think we're going to go out and educate a whole bunch of people about desal now, just using the information you've given us.
Okay.
Thank you so much. Does anybody else have any real quick farewell comments to make?
Can I have a quick question?
Yes.
Sure.
I have a very good friend who did desalination work in Saudi. You don't happen to, it's a small world, it's a tiny world. You don't happen to know Bob Wagner, do you?
I don't know Bob Wagner that I know of, but I was
Okay,
in Saudi.
that's
I was in
fine.
Saudi
I
twice in the
just
last
always
couple months.
check, I always check things like that because it's a tiny world. Like I know your daughter and I love her. And so, you know, small world.
Okay, well, good. Well,
Thank you.
Well,
This was
I'm-
wonderful. I really
Okay.
appreciate it.
Katie, thank you for coming. I think it's pretty cool. You get to see your dad being a hero for us.
Oh, I get to see that every day.
Oh, wow.
oh my God.
He knows I'm joking.
Thank you
Thank
again,
you
Tom.
for allowing me to sit in,
Okay.
and some of my league members, we really appreciate being a part of this.
Oh, thank you for having,
Thank
I
you,
mean, it was Dawn, thank you for arranging this. She said
Yeah.
it'd be good, but I had no idea it was going to be fantastic. It was fantastic. Thank you very much.
Okay.
Thank you.
Well,
Really
good. Glad
appreciate
you liked it, and good luck with your with the league out there.
Oh, hey, we do our best. We do our best.
Okay.
Oh, Mary Ellen says she feels so much smarter now. I think that's a great summary. Thank you, Mary Ellen.
Okay.
Thank
Okay.
you. Okay,
Bye.
we're going to go on to the rest of
Goodbye.
our meeting now. Thank you. The
Bye.
people from Texas don't have to stay, but they're welcome to, but they don't have to. All right, moving on. Oh, that was excellent.
Yes.
That was excellent. Okay, we're going to do the updates real fast now of the stuff that we're tracking. What I wanted to tell you from the County Water Authority, they had their final meeting of the year on November the 17th, which was their November and their December meeting. And the things that came up that I thought were really significant is they have commented, they actually hired a consultant to comment on the tunnel in Northern California. They have some very serious questions about the proposal that is currently on the table right now. They think it might be too big. And it was very interesting to contrast the consultants' comments with those that Metropolitan made, because as you can imagine, Metropolitan was a lot more excited about it than San Diego was. There were questions asked during the board meeting about whether San Diego should be paying for that tunnel because we take something like 6% of our water from the State Water Project now. And there is a real economic, gigantic, actually, commitment that's being made by Metropolitan. So we'll see how that plays out. And the other thing I wanted to tell you about, just from our DEIR perspective from the league, the Water Authority is applying for $3 million to get money for direct install of conservation things into the houses of low-income people from the Urban Drought Relief Grant Program. And that would be things like low-flow toilets, fixing leaks, conservation, shower heads and faucets and all that kind of stuff, so that it would be just regular. That right there would make a huge decrease in the use of water. That's it for Water Authority. Our next up is anything from Jane about local water resources? No. Okay. Mary Lou, anything on climate change, health, water?
We're continuing to reach out to organizations here in San Diego. The most recent one is the that we just discovered was the American Academy of Pediatrics San Diego chapter has a group of climate change and health, and there's also pediatricians for what's it called? Pardon me, I have to, all these different groups. Okay, Pediatricians for Clean Air, San Diego Pediatricians for Clean Air. So we're going to be following up not only with the health department, but also these other groups, which are really, really very innovative. So I'm excited about that. And we just had, just FYI, as you know, we just had COP27 and a lot of information came out of that. And I'm happy to provide information for you all about it if you want.
Maybe at our next meeting, we could have you do a COP summary for us. Carol Parker doesn't come to these meetings, so maybe you do it. Maybe you could talk to Carol Parker about it, Mary Lou.
Okay.
In January. Okay. So the drought report, I gave you the link to the drought. As you know, things are not getting any better, and they're not predicting that they're going to get any better. So that's the story on that. The Colorado River situation is really starting to tighten down. Metropolitan is now talking about mandatory rationing for every water district within its service area, which would include San Diego. And I think that's going to be real interesting to see how that works out. Rita, where did Rita go? Oh, there she is. Rita, still in the airport. Did you have anything on legislation? No, because they're not in session right now. And Don, I added you because from now on, we're going to have you do desalination. I think today you're off the hook because we had Tom, but next time, you're up, Cookie.
Okay, no problem.
Thank you. Okay, you all know that we agreed at our last meeting that we would seek a speaker on groundwater capture. And I am happy to tell you that Stephanie Gaines, the County of San Diego, who has written a paper on this for the entire county, will be our speaker on January the 3rd. So we've got that covered. And you all will remember that we decided that we will not be working on the, we're going to wait until next October and imagine a day without water in order to do our water presentation for our joint league meter. So our joint league presentation, sorry. So does anybody have any other matters or speaker ideas that they want to share with the group?
And if we're looking for future speakers, we may want to get an update from somebody at the City of San Diego on the Pure Water Project.
That's not a bad idea because they're getting ready to putting it, to going with it. Yeah.
Well, they've had some real challenges, but it would be interesting to get an update on where that's at. Yeah.
Thank you. I'll put that on our list.
If you need help contacting them, let me know.
Oh, you're going to be so sorry you said that. Anybody else? Any other suggestions? I had a thought, but unfortunately I forgot what it is, but I'll remember it next time and let you know. It's a slow decline, folks. But I was thinking, oh, that's such a great idea, Anne. But you'll get it eventually. It'll come back, I'm sure. And what did I just say that somebody was going to do in January? Because I forgot to write it down.
Don was going to start taking over desalination.
Yeah, I know. No, I knew that, but earlier in the meeting, didn't I tell somebody that we'd hear about it? Oh, it was Mary Lou. Yes, on COP27. Oh God, I need a nurse. That's all there is to it. All right. Does anybody have anything else? Then I want to wish everyone a very, very happy holiday season, and I want to thank Don again. That was the best. Don, that was just superb. I can't tell you how thrilled I am. We will absolutely be able to educate thousands of people. That was the most just clear, unprejudiced, it was just real, true information. God, I love people like that.
And I will talk to Tom. I get the newsletter that comes out every week, and as you know, I've shared a couple with you when I thought there was something relevant. I will see if he will let me share it a little broader with the team group when there's relevant stuff in
Oh,
there.
that would be so wonderful.
Everybody.
I didn't dare ask him to go that far. I was just,
Well, I didn't want to ask him in front of everybody and put him on the spot, but
no. You were much nicer about it than I was. Okay, anybody else have anything else? Thank you, everyone. Happy holidays, and let's not worry about water until
Everybody.
January.
Happy holidays to
holidays.
you guys
Yes,
too.
absolutely.
Thank you.